If atomic energy levels are like a staircase, why doesn't every electron in an atom simply rush down to the lowest step? The ground state is the atom's lowest energy state. But that doesn't mean every electron can occupy the same lowest energy orbital. So why can't they? Because quantum mechanics imposes a fundamental rule. Inside an atom, electrons don't simply occupy vague energy levels. They occupy quantum states. A quantum state is a complete description of an electron's quantum properties, specified by a particular set of quantum numbers. One of those quantum numbers describes the electron's spin. Electrons can occupy different orbitals within each shell, which describe their possible spatial distributions around the nucleus. The lowest energy orbital is the 1s orbital. For a given orbital, its spatial quantum numbers are fixed. But there are still two possible spin states. So the 1s orbital has two possible complete quantum states, one spin up and one spin down. Think of those as two separate seats. And here comes the fundamental rule. No two electrons can occupy the exact same quantum state at the same time. This is the Pauli Exclusion Principle. So the lowest energy orbital or 1s orbital can hold two electrons, one in each quantum state. Once both seats are occupied, another electron cannot occupy either of them. It must occupy a different quantum state. Which available state is lowest in energy is a separate question governed by the atom's energy structure. Pauli tells us how many electrons can occupy a given quantum state. The atom's energy structure determines the energies of the different available states. As electrons fill these available states, atoms develop organized arrangements of orbitals and shells. This is why different atoms contain different electron arrangements. And those arrangements determine how each element behaves. Without the Pauli exclusion principle, electrons would not be forced to occupy different quantum states. The familiar shell structure of atoms would disappear, fundamentally changing the structure of matter. There would be no structured electron shells, no periodic table, no chemistry as we know it. Most importantly, the electrons in the outermost occupied states determine how atoms interact with one another. These outer electrons can be shared, transferred, or rearranged when atoms come together. And that is the beginning of chemical bonding. A simple quantum rule ultimately determines the structure of atoms and lays the foundation for molecules, materials, and life itself.